Welcome back to the conclusion of our overview of the course, Fundamentals of Operating Systems. This series of lectures is based on the textbook Operating Systems Concepts, 10th edition, by Abraham Silberschatz, Greg Gagne, and Peter Galvin. I'm very grateful for the resources that the authors and the publishers provided for this series. Thank you very much to everyone. So let's finish this overview up. Virtualization is a technology that allows us to abstract the hardware of a single computer, the CPU, the memory, the disk drive, network interfaces, cards, the whole works, into several different execution environments, thereby creating an illusion that each separate environment is running on its own private computer. In other words, virtualization allows us to take one physical computer and turn it into multiple virtual computers, with each of those virtual computers looking like a physical computer on its own. These environments can be viewed as different individual operating systems, for example, Windows and Unix, that may be running at the same time and may interact with each other. So on your virtual computer, you may be able to bring it up as a Windows system or a Unix system or a Linux system. It's three different computers in one. A user of a virtual machine can switch among the operating systems in the same way that a user can switch among various processes running concurrently in a single operating system. Like you switch from your Word app to your Excel app and so forth. Within data centers, virtualization has become a common method of executing and managing computer environments. When I was managing the system, our server room at one time just had numerous separate computer systems, each one serving some different application or service. And as we gradually converted to virtual systems, the server room became less and less crowded with servers because a physical machine was now emulating mutual virtual machines. Now let's talk about the way data are structured in the system. Lists, stacks, and queues, for example. An array is a simple data structure in which each element can be accessed directly. Main memory is constructed as an array. If the data item being stored is larger than 1 byte, then multiple bytes can be allocated to the system, and the item is addressed as item number and size. But what about storing an item whose size may vary? And what about removing an item if the relative positions of the remaining items must be preserved? In such situations, arrays give way to other data structures. After arrays, lists are perhaps the most fundamental data structures in computer science. Whereas each item in an array can be accessed directly, the items in a list must be accessed in a specific order. That is, a list represents a collection of data values as a sequence. The most common method for implementing this structure is a linked list in which items are linked to one another. Linked lists are of several types, as you can see from this slide. Linked lists accommodate items varying in size and allow easy insertion and deletion of items. One potential disadvantage of using a list is that performance for retrieving a specified item in a list of certain size is linear, as it requires potentially traversing all the elements of that size in the worst case. A stack is a sequentially ordered data structure that uses the last in, first out principle for adding and removing items, meaning that the last item placed in the stack is the first item removed. The operations for inserting and removing items from a stack are known as push and pop, respectively. An operating system often uses a stack when invoking function calls. Parameters, local variables, and the return address are pushed onto the stack when a function is called. Returning from a function call pops those items off the stack. A queue, in contrast, is a sequentially ordered data structure that uses first in, first out principle. Items are removed from a queue in the order in which they were inserted. While you and I may hate queues like standing in line at Disney World, they work really well in operating systems. For example, jobs sent to a printer are typically printed in the order they were submitted. As we find out when we study processor management, tasks that are waiting to run on the available CPU are often organized in queues. A tree is a data structure that can be used to represent data hierarchically. Data values in a tree structure are linked through parent-child relationships. If you've taken a database course, you should be very familiar with this. In a general tree, a parent may have an unlimited number of children. In a binary tree, a parent may only have two children, which we term left child and right child. A binary search tree additionally requires an ordering between the parent's two children in which the left child is less than or equal to the right child. This figure that you see on your screen shows an example of a binary search tree. A hash function takes data as input, performs a numeric operation on the data, and returns a numeric value. Remember that data is a series of zeros and ones, so it is possible to perform a mathematical operation on a binary number. This numeric value can then be used as an index into a table, typically an array, to quickly retrieve the data. Whereas searching for a data item through a long list can require quite a number of comparisons, using a hash function for retrieving data from a table can be instant, depending upon the implementation details. Because of this performance, hash functions are used extensively in operating systems. One potential difficulty with hash functions is that two unique inputs can result in the same output value. That is, they can link to the same table location. We can accommodate this hash collision by having a linked list at the table location that contains all the items with the same hash value. Of course, the more collisions there are, the less efficient the hash function is. One use of a hash function is to implement a hash map, which associates keys to value pairs using a hash function. Once the mapping is established, we can apply the hash function to the key to obtain the value from the hash map as in the figure on your screen. For example, suppose that a username is mapped to a password. Password authentication then proceeds as follows. A user enters her username and password. The hash function is applied to the username, which is then used to retrieve the password. The retrieved password is then compared with the password entered by the user for authentication. A bitmap is a string of a certain number of binary digits that can be used to represent the status of that number of items. Suppose we have several resources and the availability of each resource is indicated by the value of a binary digit. 0 means that the resource is available, while 1 indicates that it's unavailable. The value of a certain position in the bitmap is associated with the resource at that position. For example, consider the bitmap shown below. Resources 2, 4, 5, 6, and 8 are unavailable. Resources 0, 1, 3, and 7 are available. The power of bitmaps becomes apparent when we consider their space efficiency. If we were to use an 8-bit Boolean value instead of a single bit, the resulting data structure would be 8 times larger. Therefore, bitmaps are used when there is a need to represent the availability of a large number of resources. A medium-sized disk drive, for example, might be divided into several thousand individual units called disk blocks or sectors. A bitmap can be used to indicate the availability of each sector. Well, this unit has been quite a load. Essentially what we have done is we've talked about the entire course in a week. That's quite a bit of information. And then you probably went cross-eyed or got confused a number of times during the process. Now we're going to start getting into the nitty-gritty of operating systems. And I believe you'll find that the subsequent units will have a little more clarity and a little more detail and give you a little more understanding about the topic. So be patient and keep after it, and we will move on to something new.